Hello everyone. Let us now start the session on heat treatment process in material science 18ME 34. Okay. So in the previous session, the brief introduction regarding the heat treatment process, different types of heat treatment process has been explained to you people. Now let us take one by one the heat treatment process. See, we know heat treatment is a combination of heating and cooling the materials at a particular temperature, then holding the material composition at that temperature over a period of time so that the mixture or the microstructure formulation be initiated, and at the end you are going to cool the material composition which was heated to the room temperature at different types of cooling rate as per the requirement. Okay. So in that particular case we have two types, one is full heat treatment, another one is surface heat treatment. So under full heat treatment process, the first type of process which is majorly used in steel industries, particularly for steel composition, is annealing process. Okay. So what do you mean by annealing? So annealing is a full heat treatment process wherein the entire volume of the material is heated to a particular temperature, held at that particular time over that particular temperature over a period of time, so that the necessary movements of atoms is being attained, and at the end you are going to cool the entire composition at a very slow cooling rate to the room temperature, so that the required type of component or required type of composition is being achieved. Okay. So in this particular class we are going to study different types of annealing process, the concept of recovery, recrystallization and grain growth. Okay. So the major purpose of going with annealing is that it has to result in reducing the hardness, improve the machinability and improve the toughness. So it improves the toughness by facilitating the process of cold working. See, whenever we go with the material processing, we do concentrate on two things. One is hot working, another one is cold working. Okay, so this hot working and cold working is going to be assessed based on the temperature at which the material is going to be considered during its operation or processing. Okay, we are going to study it in detail from now. So considering these three parameters, annealing has resulted in better heat treatment process that leads to better microstructure development in the material, proving these three parameters that can be considered for any of its further application. Okay. So the next topic is the different types of annealing here. So here in different types of annealing, so we are going to concentrate the time and temperature parameter, because to what extent you are going to heat the material composition and to what extent you are going to keep the material composition at that time, as well as what is the time taken to bring the material composition to the room temperature is what it matters. Okay. So you can observe here we have simply taken three representations or three types of annealing process for the representation here. See, along y-axis it is temperature, along x-axis it is time. So with respect to time, there is increase in the temperature for a particular type of process, and once that particular temperature is reached, the same material is kept at that particular temperature over a period of time. And thereby, once it is kept for a period of time, what we have done is we have concentrated on reducing the temperature of that particular composition. Again, this reduction is also with respect to time. So you can be considering a very fast reduction in the temperature, maybe by quenching as such, but here in particular to annealing process, it is a very slow cooling rate which is employed to bring the material to its room temperature condition, so that the final part is ready. Okay. So in annealing we have three parameters or three type of temperature platform wherein we have to study here. Okay. The first one being upper critical temperature, second one being the lower critical temperature, and the third one it is with respect to the composition wherein the material is considered. So in this particular study we have considered three parameters. One is upper critical temperature, lower critical temperature, and the third one being cementite temperature. So you can observe here in this particular phase diagram. So along x-axis it is the percentage of carbon, along y-axis it is the temperature in degree Celsius. So here you can observe 0.8 percentage of carbon. So if you can just recall the phase composition here, if the percentage of carbon is 0.8, you are going to say it as eutectoid composition. Okay. In this eutectoid composition, observe the phase transformation here. This is only for the purpose of illustration or understanding. See here, along 0.8% or eutectoid composition, we do have the composition of perlite as the eutectoid composition, and with respect to that perlite, we have different notifications being identified. So gamma, alpha. So obviously it is the composition of iron and carbon here that leads to the formation of different types of steel. Okay, so we have the line A1, okay, the line A1 which is represented along the horizontal axis, that is along x-axis horizontally, and that A1 is accountable for 727 degrees Celsius. So here this 727 degrees Celsius along A1 is considered to be the lower critical temperature. What do this lower critical temperature represent? You can observe in this drawing itself. So below the A1 line or below the temperature 727 degrees Celsius, the entire composition consists of no austenite present. So we have only alpha plus perlite, okay, or perlite or cementite plus perlite, whereas we don't have the composition of, or we don't have the phase in gamma, that is austenite. So how do we define this? So the lower critical temperature is a temperature below which the steel consists of no austenite in its structure. So what about the upper critical temperature now? See here, we have a A3 line representing, okay, in this particular drawing, that results in the upper critical temperature formation. Means to say that the line joining from 912 degrees Celsius to the eutectoid composition is represented by A3 line, which represents the upper critical temperature. Means to say that above A3 line or above the temperature, you are going to identify the solution completely in the austenite phase. So you can observe the entire representation here. So above A3 line, the entire solution is austenite in its microstructure. So the upper critical temperature is also considered as the recrystallization temperature, which leads to the concept of hot working and cold working here. Means to say that whenever we go with the condition of the cold working or hot working, we are going to define the temperature called as recrystallization temperature. Means to say that when the material is taken above recrystallization temperature or above upper critical temperature, we are going to say the material is working in hot working condition. Below the recrystallization temperature, we are going to define the material working in the cold working condition. Okay. So, and the third point is the ACM line, which represents the cementite line that is going with the temperature that leads to the formation of eutectoid composition in the representation. So, this is specific to whatever the composition wherein we take, but uniquely we have to target the upper critical temperature and lower critical temperature in any of the composition, wherein upper critical temperature leads to the identification of the austenite phase above it, whereas in case of lower critical temperature, you are not going to get the identification of austenite solution below to it. Okay, so this is something called as upper critical temperature and lower critical temperature. And so to go with the briefing of the different types, so annealing is a process wherein you are going to heat the composition, retain the composition for a period of time, then going with the cooling up of that particular composition at a very slow rate so that the required type of microstructure is achieved. Okay, so remember the terms like upper critical temperature, lower critical temperature. So I have written the same here for reference. Upper critical temperature above which steel is completely austenite, and it is also called as recrystallization temperature. Next comes lower critical temperature below which the steel consists of no presence of austenite. And last one is the cementite temperature ACM, which is again dependent on the composition that leads to the transformation of temperature from one particular range to the eutectoid composition, or to say the lower critical temperature. But here in this particular representation, you can observe the upper critical temperature, lower critical temperature and cementite line meet at one particular point, okay, for eutectoid composition. Okay, so this is about the brief introduction to the annealing process. Okay, now let us take different types of annealing process. The first type of annealing process is recrystallization annealing. Okay, so here in order to make the comfortable understanding of annealing process, we have taken different parameters that leads to the understanding of different types of annealing. So we have taken the major purpose, the temperature range in which it has to be considered for heating, then holding time wherein the temperature which leads to the keeping the composition at that particular temperature, and followed by the different types of cooling and the application. So here you can observe we have taken three types of annealing process here. One is recrystallization, full annealing and subcritical annealing. So let us go one by one. See, the major process of understanding the recrystallization annealing is to improve the ductility and to remove the strain hardening. So here, see, whatever the way wherein we treat the material or treat the composition of a particular steel is such that it gives you the better properties than the existing one. So here, for any existing condition of a steel composition, so in order to improve the ductility and remove the strain hardening that is due to the material formation or material kept under loading condition which initiates the strain hardening in it, okay, you are going to consider the material for a heat treatment called as recrystallization annealing. So here the temperature in which the composition is to be heated to improve the ductility and remove the strain hardening is above the recrystallization temperature or above the upper critical temperature. So you have to heat the specimen above the upper critical temperature and you have to hold the specimen based on the thickness. So based on per millimeter of thickness, you have to keep the holding time as 2 to 3 minutes. Means to say that for 1 millimeter thickness specimen, you have to keep the holding time as 2 to 3 minutes. So now, depending on the thickness of specimen, we are going to keep the holding time as such, and thereby the cooling type is a slow cooling process that leads to the improved ductility parameter and removing of strain hardening in the material. So the basic applications wherein you can find is in steel wires, sheets and strips. So it is basically a very nominal applications wherein we are going to account the entire steel for. Okay. So when it comes to disadvantages with respect to recrystallization annealing, there is no much disadvantage being identified because everything will be under controlled atmospheric condition. Okay, so next comes the full annealing process. So what is the main purpose of going with full annealing process? So full annealing process improves the ductility and removes the internal stresses that are developed during the processing or during the manufacturing of that particular component. So that particular component, what it is being manufactured, will be subjected to heat treatment considering full annealing process or parameter such that its internal stresses as well as is removed as well as the ductility is being improved. So here the temperature is kept above the upper critical temperature. So basically between 940 degrees Celsius to 960 degrees Celsius. So you are going to heat the specimen between 940 to 960 degrees Celsius such that that results in improving the ductility as well as removing the internal stresses built in that particular specimen or the material composition. So the holding time results based on the size and shape. So here the holding time exceeds to that of recrystallization annealing. It is not with respect to per millimeter of thickness is leading to 2 to 3 minutes of holding time. It is not like that. So based on the size and shape, you are going to keep the holding time more than that of recrystallization annealing process. Next comes the major thing, that is very slow cooling rate is being implied in the full annealing process. That even leads to one of its disadvantage. You can just note here. So it is expensive because of long cooling process. So since very slow cooling process is being initiated in full annealing process, it becomes a very expensive process, and this cooling rate is very high when compared to recrystallization annealing. So one of the major applications wherein the full annealing process is considered is based on hypoeutectoid steels. Means to say that when the percentage of carbon is greater than 0.8, you are going to call it as hypoeutectoid steel. Okay, so this is something regarding the full annealing process, followed by the last one, subcritical annealing. So subcritical annealing is a process wherein it is considered for improving the strain, to remove the strain hardening and to remove the internal stresses as well. So along with the same type of the purpose for both the types of annealing here, again subcritical annealing is also one of the type of annealing that leads to removing the strain hardening and internal stresses, but the method is different. Okay, it is not as like full annealing or recrystallization. Here the temperature wherein you are going to consider is, note, below the lower critical temperature. Here and all it is above the upper critical temperature, whereas in subcritical annealing it is below the A1, that is A1 represents lower critical temperature. So below the lower critical temperature means it should be lesser than 727 degree Celsius. So here it is mentioned it is 650 degrees Celsius to 700, means to say that it is below the lower critical temperature, that is less than 727. So it is 650 to 700 degrees Celsius wherein the material are going to be considered for its heating. And then comes the holding temperature. Again here holding temperature is again a very long period of time, and thereby it results the better formation of microstructure. And the cooling rate. So here, since the material is not heated above the upper critical temperature, means to says that since the material is heated below the lower critical temperature, cooling rate will not be of that importance here, because the temperature in which it is been considered results in gradual cooling to the room temperature. Okay, so cooling will not be of that importance, but the application is found in steel wires, steel sheets and steel stamping units. So here what happens, though we get the ideas of the recrystallization and the subcritical annealing going with steel wires and steel sheets, it depends on different types of grade. Okay, so it is not same type of application is being defined here. It depends on grade here. Okay, when the material is considered below the lower critical temperature, we are going to define the material under cold working condition. Whereas since we have greater than the recrystallization temperature here in recrystallization annealing, so above the recrystallization temperature means above the upper critical temperature, then the applications wherein we are going to identify will always be under hot working condition application. Okay, so these are the first three types of annealing process. Now let us take the remaining two types. Coming to the next two types of annealing, we have partial annealing and we have spiritizing annealing. So here with respect to the other three types what we have studied, so it is all one stage of processing of the entire materials so that it leads to the better properties and better microstructure. Whereas in case of partial annealing and spiritizing annealing, there are different stages wherein the same specimen is being considered to give better machinability or improved machinability property. So you can observe here in partial annealing, the purpose is to improve the machinability, and here the specimen is treated in two stages. So in stage 1, so you are going to heat the specimen from 940 degrees Celsius to 960 degrees Celsius. So that is the temperature range wherein you are going to heat the specimen. Next, what is the holding time? So when the temperature of that particular specimen is between 940 to 960 degrees Celsius, you have to hold the specimen at that temperature till the austenite phase is obtained. So till the austenite phase is obtained, you have to hold the specimen between 940 degrees Celsius to 960 degrees Celsius, followed by the cooling type. So what is the cooling type involved here? Here the specimen at that particular consideration is rapidly cooled to below the lower critical temperature, that is A1 temperature. So the temperature is to be heated between 940 to 960 degrees Celsius. You have to keep the specimen till the complete austenite phase is obtained, and thereby you are going to include the rapid cooling, that is the sudden cooling process, such that the lower critical temperature below the lower critical line is attained. Okay, next what you are going to do for the specimen which is being considered in the stage 1, the same specimen is to be taken for the stage 2 now. That is, the specimen which is now cooled, rapidly cooled below A1 temperature line, that is below lower critical temperature line, is to be considered for the again heating process of the 600 to 700 degree Celsius. Now what is the condition of holding time? So now here we have the austenite phase in the entire material at the first stage. So now we have to keep the specimen between 600 to 700 degrees Celsius such that the austenite gets converted into perlite. Okay, the austenite should convert into perlite. Then the cooling type is the air cooling process, which is normally cooled in the presence of the natural air. Okay, so that is where the cooling process is considered, and hence you are going to get the perlitic formation of structure when it goes with the partial annealing. That is, you are going to heat the or consider the annealing process at 2 stages for the same specimen. So the application is considered in alloy steels. One of the major advantages is that it is less expensive than the full annealing process, and the major disadvantage is that this is the process which is not suitable for heavy components. Okay. Moving on with the last type of annealing, that is spiritizing annealing process. Again, the purpose is to go with improving the machinability. Here we are going to consider the specimen for 3 stages. Okay, so this is applicable for the high carbon steel, tool steels and alloy steels, and these are the type of steels which can be considered for spiritizing annealing process. And here it is a 3-stage process, as like the partial annealing. So at the first stage you are going to consider the specimen to a temperature below A1, that is lesser than the eutectic temperature, that is between 650 to 700 degrees Celsius. Followed by you are going to hold the specimen at that temperature 2 to 3 minutes per millimeter of thickness and even 40% more duration. Okay, followed by the cooling is very slow cooling process. So it is normal cooling process which is be accountable at stage 1. Now what we do, the specimen which is treated in the stage 1, the same specimen is to be taken and you are going to heat it above and below 727 degrees Celsius. Here it is below lower critical temperature, that is below A1. Okay, whereas here it is above and below the lower critical temperature 727 degrees Celsius. How do we achieve it? You are going to heat it and cool the same specimen alternatively, so that you are going to reach above and below 727 degrees Celsius in the temperature range. Next comes the holding time. The holding time is as similar to the stage 1. It is again 2 to 3 minutes per millimeter of thickness and plus 40% more holding time based on the thickness. And the last is cooling. Again, like stage 1, it is slow cooling process, normal cooling process included in the stage 2 here. And coming to the last and final stage of spiritizing annealing, the same specimen which is been now treated in the stage 2 is taken for the stage 3, wherein it is heated to a temperature of 750 to 780 degrees Celsius for eutectoid composition, that is 0.8% of carbon in steel. Whereas greater than 0.8% of carbon, the heating ranges goes beyond it, that is 780 degrees Celsius to 800 degrees Celsius. So based on the percentage of carbon, the temperature range increases. Next comes the major part, holding time. So as the name itself suggests, spiritizing annealing, the holding time at the last stage is such that the complete shape of carbide gets converted into spheroidal shape. So entire carbide shape should get converted into spheroidal in its nature. Till that spheroidal nature is attained, you have to keep the specimen at this particular mentioned temperature range based on the carbon content. Now comes the cooling. So the cooling is furnace cooling or very slow process of cooling, wherein you are going to turn off the furnace and leave the process to cool, or leave the entire specimen to cool till it reaches the below A1, that is lower critical temperature. So as it is suggested, it is applicable for high carbon steel, tool steels and alloy steels. So these are the contents that are to be studied and understood regarding the process of annealing. The next topic goes with recovery, recrystallization and grain growth. So this is a topic which is going to be studied or understood based on the behavioral changes or the changes which happens inside the material, okay, due to the heat treatment process. Okay, so as we come across the term called as recovery, recrystallization or the grain growth, so it seems to be a very familiar word when we go with the understanding of these 3 parameters, but when we are explaining the same, we have to be very technical, because there are plenty of changes that will be considered in the material due to the heat treatment process. Okay, so keeping heat treatment process, so let us go with the understanding of recovery, recrystallization and grain growth. So here the questions in case of your exams may be expected in the form of short notes or in the form of a brief description on these 3 parameters. Okay, so the first one goes with recovery here. So during recovery, internal stresses are relieved dislocations are rearranged into lower regions, and consequently there is a partial restoration of its original properties. See, as the name recovery itself suggests, you are going to recover the minimum amount of properties once the material is being loaded at a particular condition. So here what happens, when the material is heated or when the material is considered for heat treatment, so thereby what happens, the concepts of recovery comes into picture when there is the removal of internal stresses, or there is a relief of internal stresses in the material during the heat treatment process. See, as we go on with the increase in the temperature, these are the three stages which are going to be assessed over a behavior of particular material. So as the name itself suggests, recovery, so there has to be a minimum, at least minimum amount of its original properties that has to be recovered when the material is being heated or it is being subjected to increase in the temperature. Okay, so usually the recovery stage, when it comes to the comparison of recrystallization or grain growth with the increase in temperature, so recovery is always expected at the start of the increase in the temperature wherein the material is being subjected to. Okay, so dislocations are rearranged into lower regions, means to say that as soon as we heat the material to a particular temperature, and as soon as we keep the material at that particular temperature, so anyway we know that we cannot create or prepare a material with 100% dislocation free. So there will be some amount of dislocation, there will be some amount of error in the production of a particular material. So thereby what happens, due to this particular heat treatment at the recovery stage, that is at the start of heat treatment process, there will always be a chance of moving the dislocation to certain lower regions than the higher region. So we have to recall the concepts of first and second module here to understand the behavior of dislocations and different types of dislocation. So to remember, keep this in mind. So internal stresses, those are the stresses that are developed due to the internal change in the atomic movement or the molecular movement in the entire material, which is subjected to particular type of loading condition. So once the load is removed, even when the load is removed, there will be movement of atoms or material molecules in the material. That leads to the development of internal stresses. So that internal stresses will be relieved, as well as the dislocations will be moved into the lower region. Next comes the concept of the recrystallization. Before that, there is one key point here, but there are hardly any changes in the microstructure. So since recovery stage is the initial stage of consideration in the increase in the temperature, so the microstructure will remain as it is in the almost maximum case. So you can observe this particular comparison graph here. So we have increase in temperature along the x-axis, and we have different strength properties along y-axis, which is represented here. So you can observe the first stage of consideration is taken as recovery, that is the initial stage in which the increase in temperature for a material is considered during the heat treatment process. So you can observe here, in case of recovery stage, there will be a minimum increase in the ductility of material, whereas the strength and hardness, so you can observe the variation in the color chalk written here. So the hardness and strength almost remains same. That means to say that the microstructure will not change, whereas the original properties of partial restoration of its original properties is being achieved. That goes with the strength and hardness of the material, but the ductility properties will be varied with respect to its consideration in recovery stage. Next comes the concept of recrystallization. So recrystallization is same as crystallization, but there is one particular change, because see, in case of recrystallization, you can observe the statement here. So it is just like crystallization, wherein molten metal begins to solidify, but the only difference is that the nuclei formed here, that is in the recrystallization, will be in the solid state, whereas when it comes with the crystal growth or in the crystallization process, there what happens, the nuclear formation will be in the liquid state. So as we all know, crystallization is nothing but formation of a molten metal into solid structure, maybe in the form of crystals. That is what we call it as crystal structure or crystalline crystallization, whereas so here in case of crystallization, the crystal growth is what we are going to target when it comes to material science or the behavior of material, whereas here in case of recrystallization, the only difference is, as the name itself have, re recrystallization. So it is almost similar to crystallization, but the only difference is that here the nuclei formation will be in the solid state, whereas in case of crystallization or in the crystal growth, we are going to have the nuclei formation in the liquid state. Now comes with knowing this particular difference, okay, if we do target the recrystallization process here, so we can state like this. What happens in case of recrystallization? That is what we are going to supposed to understand here in this particular concept. So during recrystallization, all old distorted grains disappear and new grains are formed while entering the last phase, which is called as grain growth. So don't confuse here with grain growth and the crystal growth. So crystal growth is due to the crystallization process here, whereas here the grain growth basically deals with the increase in the size of the grain or in the grain boundaries. Okay, so here what happens in case of recrystallization, all old distorted grains disappear. So this is the intensity of recrystallization what we are going to study here. Means to say that when all the the previously held distorted grains or the grains which are resultant due to the previously held process will disappear and new grains are formed while entering the last phase, which is called as grain growth. Means to say that during recrystallization, the X factor of the grains will be disappearing, whereas the newer formation of the grains will take place till the phase enters into the grain growth. Okay, so you can observe here in this particular figure, so there is a middle layer which is considered with the increase in the temperature here, or that is the middle range in the increase in the temperature that leads to the formation of recrystallization. So here you can observe there is increase in the ductility of a material in the recrystallization phase, whereas there is decrease in the hardness and strength. So this decrease in hardness and strength is basically due to the changeover of the old distorted grains into newer grains. So keep here, it is not the old grain, it is the old distorted grain, that is old dislocated part. Okay, it is the error which is going to be recovered here when it comes to the recrystallization phase. Now comes the concept of grain growth. Okay, here this stage is characterized by the size of grain, okay, and not by annealing temperature, because see, whenever we go with the concept of temperature here, it always deals with a particular temperature wherein the metal will be considered at its molten stage, and thereby you are going to keep the metal at that particular or the combination of materials at that particular stage, and thereby you opt for certain cooling process wherein it leads to newer formation of the material when it comes to its microstructure or different phases. So here what happens, whenever there is a such particular case, instead of the consideration of metal, there is always be a one particular point that metal will always tend to move, or the molecules or the atoms in the metal always tend to move towards its lower energy barrier. Okay, so thereby what happens, we are going to consider in that particular perspective the concept of grain growth. So this stage is characterized by the growth in size of grains and not by annealing temperature, but due to the tendency of metal to get into lower energy status by reducing the grain boundaries. So what happens, the grain boundaries is the much of concern here when it comes to growth of grain in its size. Okay, so since grain boundaries are region of higher energy, the microstructure tends to reduce the grain boundary area that results in the increased grain size. So here we are supposed to target the growth of grain in its size, not with respect to variation in the grain size due to the temperature. So basically what happens, it goes with the concepts of the grain boundaries. So I repeat, since the grain boundaries are region of high energy, the microstructure tend to reduce the grain boundary area, okay, that results in increased grain size. It is just the proportionality what we take directly or inversely proportionality pattern wherein we go with the consideration here when it comes to grain growth. Okay, so you can observe the same in this particular figure, that is the third range of consideration here. Okay, so in the grain growth, again the hardness and strength tries to be at a nominal range, or it tries to be constant with the increase in temperature, as well as the parameter of ductility goes increasing with the increase in temperature. So this is the concept of recovery, recrystallization and grain growth with respect to the concept of heat treatment process. Thank you.